Hello and welcome back. It's time for lesson 2. We're going to give a brief introduction today to solving limits analytically. What our goal is going to be today is we're switching away from the visuals. In fact, we're going to have very few visuals except for the purpose of building concepts, and we want to get to where we can do these strictly algebraically. And so what we're going to be trying to do then, I want you to keep this in mind as we go through and as you work on the assignment, is the goal is we want to be able to do a direct substitution. We need to work until we can do that. And so we're going to be dealing with some algebraic tricks that will allow us to do that. This is a brief introduction in this lesson. You'll have to be a little bit creative on your assignment to get that done. So let's get started. Okay, this is what I'm talking about when I say that we really want to do a direct substitution. Unless something goes horribly wrong, usually division by 0, then we can just go ahead and pop that little number right in there, and I think you can probably figure out that 2 times 5 minus 1 is 9, and that's all it is. That's all there is to it. Next one, same thing. Can we plug it in? Yeah, seems like we could probably square a negative. That's not a problem. Negative 1 squared, seems like 1. 1 minus 3 is 2, and boom, we're done. So what's the difference between a function value and a limit then? Because we just employed the exact process that it would take to find a function value, that is a direct substitution, and we did that to a limit. So what's the difference? Well, in this case, nothing, because of what we talked about in the last lesson. If you have a continuous function, then your function value and limit are equivalent. But the difference is, for a limit, a lot of times this number right here will not be in the domain of the expression that's given. And so with function values, when that happens, we throw our hands up and we're out of luck. With limits, we get to employ a little bit of trickery to try to figure out what the limit is. And so let's look at an example of what that can be. The first trick we're going to talk about, and the only one in this video today, is we are going to factor and cancel. This is something that comes up really commonly, especially in the early phases of learning this. And so we've got our first example here, and it looks nice, but there's a little bit of an issue. If we try to plug in a 1 right here, 1 minus 1 is 0. We're dividing by 0, and that's a real problem. So what we need to do is trick number 1. We're going to try to factor and cancel. So notice right here, the numerator, it's a difference of squares. So off we go. We're going to rewrite this. Limit as x approaches 1, but now we're going to factor it. X plus 1 times the quantity x minus 1. And we've got an x minus 1 down here in the denominator. And what do you know? Those get to cancel by. It's been fun. See ya. They're gone. And so now, once we've done that, every time we do a step, we're going to pause and ask ourselves, can I now complete the direct substitution? So popping a 1 in there, let's see, are you allowed to add 1 and 1 together? Yeah, sure, why not? Of course, it's first grade. So yeah, let's do that. 1 plus 1 is 2, this is done. Okay, so what the heck just happened? We took a function that did not have 1 in its domain, and by a simple little algebra trick, we sort of, what looks like put 1 in the domain. How can you change the domain? Well, you can't. What we're doing is a little trick. This is called a removable discontinuity, and we've actually removed part of our equation by canceling it out. Here's what it looks like visually. We call this oftentimes a deleted point. And so here it is. It actually looks like a linear function because essentially it is. It just has this one point right here, and if you trace up from this value right here to there, you'll see that at an x value of 1, it's missing a single point, and only 1 point. So that's why we weren't able to plug in 1 in the beginning, because the function isn't defined for that. We can see that here, but we're able to figure out, like in the last lesson, visually, how when we squeeze in from either side, or the information and the pattern on either side, they all lead toward that location with a y value of 2. And so that's what's going on. That's the connection between the algebra and what our visual is. So, I would encourage you now, pause the video, try each of these 3 examples, and then watch along, see how you did. Here we go. Okay, first one, we're going to factor and cancel, just like the example we had. Should be pretty straightforward. And so we're going to have x plus 2 and x minus 2. X minus 2 down below. X minus 2's cancel out, plug in the 2, and you get 4 when you do that. Second one, it's a trick question. You can't factor that, and you can't plug in a 2, so right now, there's nothing we can do about it. This does not exist. Last one, try to plug in a 7. Whoops, can't do it. That puts a 0 in the denominator. So again, does not exist. Okay? The only reason I put these in here, I don't want you to go forward with the assumption that every time you see something squared, automatically it will factor. It's amazing. A lot of students see this here, the x squared plus 4, and they assume you can factor that because it looks so similar to x squared minus 4, but it's not factorable. You can't factor that, and so we're actually stuck with our current skill on that right now. Okay. Down here I want to include a couple more visuals and a little bit more vocab for you so you can gain a little bit of an understanding of what's going on. So when you have a situation where you have a discontinuity and you cannot remove it, okay, rewind. Removable looked like this. It looked like canceling stuff out. Visually, it looks like a deleted point. We've got another example right here of a removable discontinuity where we're canceling stuff out and it lets us get an answer. That looks like a deleted point. But sometimes we can't cancel it out, like these. There's nothing we can cancel out, nothing we could do, it didn't exist. Visually, what's happening is something called a non-removable discontinuity. And here's two examples of what that could be. It could be a vertical asymptote, or it could be something like this, some sort of a jump discontinuity, or maybe like a piecewise that maybe comes up like this, has an open circle, has it filled in, and then goes like that. And so you have to physically jump to get from one point to the next point on the graph. It's not like there's one missing point. In fact, the way my teacher described it, when I took this, he said, if you have a removable discontinuity, you could fix that discontinuity by putting a single point on the graph, and there would no longer be a discontinuity there. But in a removable discontinuity, there is no single point that you can place on the graph that would fix it. So check this out. I can put in a dot right there. I did not just make that continuous. There's still a massive gap in between those points, and there's nothing I can do to fix it short of drawing a vertical line. But wait a minute. Why is it that we cannot put in a vertical line on our function? Oh yeah, vertical line test. It would totally fail the vertical line test. So that would not be an option. These are non-removable. And if you're evaluating at that point, check it out. As we trace the functions, they're not coming together because this pattern indicates infinity, this pattern indicates 0. They don't match, so the limit does not exist. Okay, I want to challenge you with one more down here before we get into our last part of the lesson. And so I'd like you to pause the video, try this one out, and see if you can get it. And here's how we do it. We're going to go limit of x approaching 1. You know what, actually I forgot something. I should always try to substitute this in first. So I should have tried that. So if I put this in, I get 1 squared, that's 1. 1 minus 1 is 0. Okay, crap, that didn't work. So I actually do have to factor it. So let's do a little bit of factoring. Denominator looks pretty simple, x plus 1, x minus 1. Let's check out the numerator, looking for numbers that multiply together to be -4, add together to be -3. Looks like we could probably go x minus 4 and x plus 1. We'll cancel out what we can. And it looks like we have x minus 4 over x minus 1. Limit as x approaches 1. And so now we try again. Plug in a 1. Uh-oh, that creates a 0. So what does that mean? I mean, we had a removable discontinuity there. We have a non-removable discontinuity at x equals 1. So that means our limit for x equals 1 does not exist. We got one more thing, and it's time to get into our assignment. Okay, and here it is. And I've got just a couple simple examples here on the board, and I've got the words that go with them. So there are some ways that we can break up limits if they're too difficult, and we can look at them in different ways. And this is going to be super helpful when we get to derivatives, we get to integrals. So the first one is the limit of the sums is the same as the sum of the limits. We've got an example here. They've got x squared plus 3x. You can break it into two different limits and solve it that way. I don't know why you'd need to with this one, but if you had something really complex, perhaps that would be helpful. Next one, the limit of products is the product of limits. That's this third line down here. It looks like I didn't coordinate them. And so if you have things multiplied together and you're taking the limit of it, you can break that into two separate exercises, multiply together their results. Same thing works with multiplied constants. You can totally factor out a constant. That is going to be a really big deal when we get to derivatives. That's going to make things a lot easier for us. And the last one, the limit of a root is the root of a limit. So if you have a root here, you can go ahead and pull that out. Okay? And that'll make things a little bit easier at some times. Okay? This was part 1 of our analytic limits lesson. We'll get into the next one next time, and I'll see you then. Bye-bye.